Good morning, students. In last lecture we had seen the optimum allocation first. In optimum allocation first we have to prove Ni is directly proportional to Ni Si upon root of Ci for minimizing variance subject to a fixed total cost. But in this case, optimum allocation second, if your cost function is like this, then we have to prove Ni is directly proportional to Ni Si upon root of Ci for minimizing total cost. Here we have to minimize total cost subject to a fixed variance. The difference between optimum allocation first and second is, in optimum allocation first we have to minimize variance subject to a fixed total cost, and in optimum allocation second we have to minimize total cost subject to a fixed variance. And here also we have to obtain the expression for Ni. So proof of this theorem. Here Ni is found such that, how to find Ni? There are two conditions. We have to minimize the total cost. So total cost is this one, C0 plus summation I running from 1 to k Ni Ci is minimum, and second condition is variance is fixed, and in stratified random sampling variance is variance of y bar st. If fixed means some v0, so this is fixed. Now we solve this problem by Lagrange's multipliers. We solve this problem by Lagrange's multipliers. Here we define phi, and after defining phi we have to take its derivative with respect to Ni and equate it equal to 0, and for that value of Ni this cost is minimum. So phi is equal to whatever we have to minimize, we have to write here. So here we have to minimize the total cost. So write down total cost here, C0 plus summation I running from 1 to k Ni Ci, plus take lambda as constant of Lagrange's multipliers and write out this condition. Write down this condition by equating it equal to 0, means send this v0 in this side, then this will be equal to 0. So variance of y bar st minus v0. We know the formula for variance of y bar st. Formula for variance y bar st, put here the formula of variance of y bar st. So C0 plus summation I running from 1 to k Ni Ci plus lambda into formula for variance of y bar st is 1 upon n square summation I running from 1 to k Ni into Ni minus Ni Si square upon Ni minus this v0. Now we had defined phi. Now consider dou phi by dou Ni. Dou phi by dou Ni. Now take derivative of this phi with respect to Ni. So here this will become dou by dou Ni of this C0 plus here it will be dou by dou ni of summation I running from 1 to k ni ci plus if we apply this dou by dou ni here, then it will going to apply here, and this will not directly, we cannot apply this directly inside this summation because the derivative is with respect to ni. Here also we cannot directly take this dou by dou ni inside this summation because this derivative is with respect to ni, means all other quantities will be constant. So here it will be lambda into 1 upon n square dou by dou ni of summation I running from 1 to k ni into ni minus ni si square upon ni minus, and dou by dou ni will going to apply for this v naught also. So we had taken dou phi by dou ni and we have to equate it equal to 0. So first find out dou phi by dou ni, then equate it equal to 0. So this is equal to, now derivative of this c naught with respect to ni is 0 plus dou by dou ni of, solve this summation first. So this will be n1 c1 plus n2 c2 plus up to nk ck. Somewhere there will be nici. So here somewhere it is nici and plus up to nk ck. Alright, plus lambda into 1 upon n square, 1 upon n square. Now we cannot directly take this inside this summation. First solve this summation. So this will be dou by dou ni of n1 into n1 minus n1 s1 square upon n1 plus n2 into n2 minus n2 s2 square upon n2 plus up to some here it is ni into ni minus ni si square upon ni plus up to last term will be nk into nk minus nk sk square upon nk. This bracket will going to close here, and dou by dou ni of this v naught will be 0. Now this bracket will going to close here. In next step we have to apply this derivative to every term. So apply this derivative to every term. So this will be dou by dou ni of n1 c1 plus dou by dou ni of n2 c2 plus up to dou by dou ni of nici plus up to dou by dou ni of nk ck plus lambda into 1 upon n square. Apply this dou by dou ni to every term, and this will be dou by dou ni of, so write down here this bracket, and dou by dou ni of n1 into n1 minus n1 s1 square upon n1 plus again we have to write here another bracket. Okay, dou by dou ni of n2 into n2 minus n2 s2 square upon n2 plus 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 up to dou by dou ni of ni into ni minus ni si square upon ni plus up to dou by dou ni of nk into nk minus nk sk square upon nk. So here this bracket will going to close here and this bracket will be going to close here. Now in next step this will be dou by dou ni of n1c1 will be 0 because there is no ni, so this is constant with respect to this derivative. The second term is also 0 plus dot dot all other terms are 0 and derivative of this ni ci with respect to ni will be ci plus 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 up to all other terms are 0 plus lambda into here it is 1 upon n square. And if we apply this derivative here, there is no ni, so this is also again 0 plus the second term is also 0 plus plus up to all other terms are 0, and if we apply this derivative to this ni, this ith term, then this will be dou by dou ni of ni square. If we solve this bracket, then this will be ni square si square upon ni minus ni si square, because here in second term this ni gets cancelled, plus 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 up to all other terms will be 0. This bracket will going to close here and this bracket will going to close here. And look at this, this will be ci plus lambda into 1 upon n square so dou by dou ni of, if we apply this derivative here, then this ni square si square will constant and this derivative will going to apply to this 1 upon ni, and here this second term there is no ni, so this is constant with respect to this derivative, so this is 0. So derivative of this is minus ni square si square upon ni square, so minus ni square si square upon ni square. This is your dou phi by dou ni. Now we have to equate it equal to 0. So consider dou phi by dou ni is equal to 0. This implies if we equate it equal to 0, then this will be lambda upon n square ni square si square upon ni square is equal to ci. Send this ni square in this side and ci in this side, so this will be ni square is equal to lambda upon n square ni square si square upon ni square, and this is ci. This ci we have same in this side. We have to find expression for ni. So taking square root on both sides, this will be ni is equal to root lambda upon n square into ni si. Sorry, there is no ni square because we had sent this ni square in this side, so there is only ci. So this will be, after taking the square root, this will be ni si upon root of ci. Alright. Now we can write this into proportion. So This implies this is your equation number 1. So this we can write Ni, we can write this in proportion because this is a constant. So Ni is directly proportional to NiSi upon root of Ci. We have to prove this one. So theorem is prove that Ni is directly proportional to NiSi upon root of Ci. And also we have to find the expression for Ni. So look at this equation number 1. Here we don't know the value of root lambda. So we have to find value of this root lambda or root lambda upon, here it will be n. After taking square root, this will be n. So root lambda upon n, we have to find value of this constant and then we have to put here. Here in equation number 1, we can write this Ni upon n as Wi. So this will be like this. Ni is equal to root lambda Wi(Si) upon root of Ci. So in this case, this root lambda is constant and we can write this as Ni is directly proportional to Wi(Si) upon root of Ci. So sometimes in theorem there may be like this, prove that Ni is directly proportional to Wi(Si) upon root of Ci. So in that case we have to make corresponding changes here. So we have to find expressions for Ni. So here take in equation number 1, take summation I running from 1 to k on both sides. So this will be summation I running from 1 to k Ni. If we take summation here, then root lambda upon n is constant. Then summation will going to apply for this NiSi upon root of Ci. Now we know summation Ni is n. So this will be n into root lambda upon n summation I running from 1 to k NiSi upon root of Ci. Now if we send this in this side, this quantity, then we will get the value of root lambda upon n. This will be n upon summation I running from 1 to k NiSi upon root of Ci. After putting this value in equation number 1, then we will get, after putting this value of root lambda upon n in equation number 1, then we will get the value of Ni, so which is Ni. So equation number 1 implies Ni is equal to NiSi upon root of Ci upon summation I running from 1 to k NiSi upon root of Ci into n. So this is the expression for Ni, okay, small Ni in terms of capital Ni. So or if we divide in this side to numerator and denominator by n, then this will be Ni upon n. Here it is also Ni upon n. Ni upon n will be Wi. So this expression will be like this: Wi(Si) upon root of Ci upon whole divided by summation I running from 1 to k Wi(Si) upon root of Ci into n. So this is the expression for small Ni in terms of Wi. So in some examples, value of capital Ni is given. So in that case we have to use this formula, and in some examples value of Wi's are given. So in that case we have to use this formula. Now we will move to this remark. We know that under proportional allocation Ni is directly proportional to Ni. This means from larger strata take large number of observations. So if small Ni means ith strata sample size and capital Ni means ith strata size. So from larger strata take large number of observations. From larger strata take large number of observations. In Neyman's allocation, Ni is directly proportional to NISI. This means from larger strata take large number of observations. And this SI means consider this as a variance. So from the strata having larger variation take large number of observations. Suppose in a strata there is a large variation. So from that strata we have to take the large number of observations. Third remark is under optimum allocation we know in optimum allocation first and optimum allocation second also Ni is directly proportional to NISI upon root of Ci. So this means from larger strata take large number of observations. From a strata having larger variation take large number of observations and take small number of observations if cost per unit in the ith strata is large. Ci means cost per unit in ith strata. So this is in divide. So take small number of observations. So if Ci is more then Ni will going to decrease. So this means take small number of observations if cost per unit in the ith strata is more. So if cost is more then reduce your sample size. Thank you.